Let's see here. I'll get started. Heavenly Father, we thank you for this day again. I thank you for this class, and just ask you to just bless our work today. Help us to glorify you, and we do, Lord. In your name I pray, Lord Jesus. Amen. So the top hat code is 4300 for what that's worth. Come on, marker. And I'll let you guys add another day to this sheet here. So last time I think I showed you excuse me, that the solution, last time we learned that the solution set of d minus lambda to the mth power on y equals to 0 is y1 equals e to the lambda x. I'm going to use t, if you guys don't mind. Lambda t. Y2 equals t e to the lambda t. Y3 is t squared e to the lambda t, all the way up until we get to yn equals t to the n minus 1 e to the lambda t, given that lambda is a scalar and m is some natural number, all right? And also the derivative operator in my current context I'm saying is ddt. So that's a result. I gave you proof of that last time, and I gave you a partial derivation, but I'd kind of like to complete. I was kind of mid-thought, and I got worried about time last class, and this always happens Monday, Wednesday, Friday. But let me derive the derivation continued. So there's a difference between a derivation and just a plain proof, right? Like you can prove something works in differential equations by just writing down the answer and then plugging it in and showing it works, right? That logically is sufficient to show that we have a solution, but it's a little bit unsatisfying because sometimes you want to you want to derive it, right? So last time I showed you how we could derive if we have d minus lambda y equals to 0. We're like, oh, well, that's dy dt, right? Equals lambda y, which gives us dy over y. Integrate that, lambda dt, and an algebra step later, you've got y is equal to like c1 e to the lambda t, right? And then I also told you that if we had d minus lambda squared y equals to 0, I guess I need to I need to start having quizzes at the start of class again, I guess. I don't know, this is what, 5, 10 people, after the first 5 minutes of class? I don't know. I'm trying not to care, but, yeah, wait a minute, I'm wrong. It's only 8:18. I'll chill. So, but this is why I hate teaching at 8:15. It makes me say things I wouldn't say in any other time of day. I hate 8:15. Anyway, d minus lambda squared y equal to 0. So I said, well, we could look at this instead as d minus lambda times z equals to 0, right? Where z is equal to d minus lambda y, right? And if we make that substitution, because this is just, two things composed, well, then this gives us, of course, we do the same thing we did up there, and we get, z is equal to c1 e to the lambda t, but then what do we get? Well, then we've got dy dt minus lambda y is c1 e to the lambda t. See, because that's the substitution here, right? And then how do you solve that? You multiply by the integrating factor, right? e to the minus lambda t you get that. Reverse product rule this thing. Integrate both sides with respect to time. And we get e to the minus lambda t. Y is equal to c1t plus c2. Now I did all this last time, but I'm going through it again. So t e to the lambda t plus c2 e to the lambda t, right? So there we go. We derived the m equals. So now we've seen that we get these two, right? I've derived those. And we can derive the third one in the same way. Let's see how that goes. So m equals 3. So we'd have d minus lambda cubed y equals to 0. So look at this as d minus lambda operating on d minus lambda squared y equals to 0, right? And we make a substitution, call this thing, for lack of imagination, z. So you got d minus lambda acting on z equal to 0. We can solve that, as we've discussed. That gives us z equals c1 e to the lambda t. But then we can make a w equal to d minus lambda y substitution, right? And with respect to this substitution, we see we've got d minus lambda acting on w equal to z. So basically I'm saying if I do I need to write it out? But so I'm saying is if the z is d minus lambda squared, I can define w as d minus lambda times y, and then this becomes d minus lambda times d minus lambda y, but I called that w, so I have this. But we already know what z is, right? So this is c1 e to the lambda t. And then, so I've got dw dt minus lambda w equals c1 e to the lambda t. Again, we do the integrating factor method, right? So e to the minus lambda t dw dt minus lambda e to the minus lambda tw equal to c1. Reverse product rule. Now, so for you math majors in here, there's probably like a more elegant way to do this, but I'm not trying to be clever at the moment. I'm just trying to show you guys a straightforward method to derive these solutions, all right? But of course, C1 t gives us what? We got what? We got e to the minus lambda tw equals C1 t. I feel like I could have just written this down because I already worked this out, right? Yeah, thank you, plus C2. So let me not write down here. So we get w. I should have just written this down because we just worked this through, right? Excuse me, guys. E to the lambda t plus c2 e to the lambda t. I mean, I feel like I have a strong sense of deja vu. We've been here before, right? But what's the difference now? Now we're not at the end, right? We're not back to y. You know, in the m equals 2 case, that was the end of the road. This was, you know, we were done. We'd found everything there was to find for m equals to 2. Now we're working on m equals to 3. There's still more to do, see, because this is equal to d minus lambda acting on what? By construction y. So what we got, yet again, is dy dt minus lambda y is equal to c1t e to the lambda t plus c2 e to the lambda t. Bless you. And guess what we're going to do? We're going to multiply by the integrating factor, because this is a linear. And the integrating factor here is e to the minus lambda t. what happens when you multiply by integrating factor over here? You just get just that, right? Reverse product rule this thing. And integrate both sides with respect to time. And what do we get? We get, I'm going to skip a step, y equals to, 1/2 c1t squared plus c2t plus c3 all times e to the lambda t, right? Now, so this tells me that I have y1 of e to the lambda t. I've got my y2 of t e to the lambda t, and y3 of t squared e to the lambda t as solutions, right? Any questions before I go on here? Can you see that we can just keep doing this, right? And what's going to happen is if we make these successive substitutions, we're going to always end up with, like, basically dy dt. Like the general thing we're going to end up with is just dy dt minus lambda y is equal to, well, let me not. I think I've done enough. I'm going to stop there. Unless there's a question. So some lingering questions. We've used this math in the case that lambda is complex. Is that reasonable? Like, are these calculations I'm making, do they still make sense when lambda is complex? I heard a yes. I heard a So it's kind of a mixed bag. If lambda is equal to alpha plus I beta, then e to the lambda t is e to the alpha plus I beta t. All right? And that is e to the alpha t, e to the I beta t, which we can work out as e to the alpha t cosine beta t plus I e to the alpha t sine beta t. How do you differentiate a complex valued function of a real variable? Like, what does it mean to differentiate e to the lambda t in this context? What are we talking about? Well, we'd have to differentiate this guy, and then this one. So I don't know if you understand why this is true, but really all I'm doing, in calculus 3, we talk about differentiating like a path to find the velocity. How do we do that? We differentiate the first component, and we differentiate the second component, and we just do them separately, right? It's the same thing here. Like, a complex valued function of a real variable is exactly a formula for a path from, like, R into R2. The complex numbers are R2. You can think of it this way. A plus IB, you could think of it like this. Geometrically, it's just A comma B. So whenever you're working with a complex number, you're really just working with something in the plane. And this is how we think about it, the calculus of it. We just do it component-wise. So this is just the definition of differentiation here. All right? Then what do you do? Usually I assign this as a homework. Did I do that? I don't remember. At the risk of doing your homework, let me continue. So this is a product rule, right? Alpha e to the alpha t cos beta t minus e to the alpha t beta sine beta t. Why is there a beta there? Because it's a constant? Well, that's kind of part of it, but why is that constant there? What's that? Chain rule. Chain rule. That was, those are the magic words I was looking for, yes. So we have the chain rule 4 times. We have the product rule 2 times, right? And then what you do is you factor an alpha out. Oops. So we factor alpha out, we get these two terms. And then we can factor I beta out. And this takes a little bit more imagination, the factoring out the I beta. One part doesn't take any imagination at all, this term right here, right? That just gives us e to the alpha t cosine beta t, great. But this one here takes a little bit more imagination. We have to see minus 1 equals to what? I squared. So take one of those, pull it out here, take another one, put it here. If I'm doing your homework, my apologies, but we should all understand this is why it's okay to do what I'm saying we can do. What is this, though? The thing in the parentheses, both. What are they? Recognize what they are. What are they? See, I mean, I wrote it right here, right? This is precisely e to the lambda t. And this again is e to the lambda t. I told you it was tricky. So alpha, you got it? Okay, cool. Alpha plus I beta e to the lambda t, also known as lambda e to the lambda t. So don't take it lightly when I tell you, oh, this works in the complex case. That's not obvious. It's all of the calculus I just did. All of that calculus is rolled into extending calculus to the complex number system. Calculus in the complex number system plays super nice. And this is wonderful, because this means that all the derivations I did at the start of class are equally legitimate in the complex context. But that solution set, instead of being a set of m real solutions, it's a set of m complex solutions. Each one of those being linearly independent in the complex sense, which actually ends up meaning we have 2m real solutions, as we'll see. Okay, so I've given you a proof last time of sorts. I've given you a derivation this time, I hope. There's still some theoretical legwork we need to do. How do we know that this set of functions is linearly independent? Because we need that it's linearly independent if this is going to be a full account of the solution set to this problem. So how do we check linear independence? Over here. Wronskian. Let's do it. Let's calculate the Wronskian. Tell you what, I'm going to do it for 3 of them, and then we'll decide whether or not we want to do it for n. All right? So let's do e to the lambda t, t e to the lambda t, t squared e to the lambda t. So this would be the determinant of, let's see here, we do the top row is the function, right? Ooh, yowzers. I'm just thinking about what's coming. The first one doesn't hurt too much. Differentiate, right? And then here we've got 1 plus t lambda. I'm going to factor the e lambda t out if you guys don't mind. And down here I've got a oh no, 2t plus t squared lambda e to the lambda t. I'm doing the whatchamacallit, the product rule in my head, and I'm going ahead and factoring out. I regret not doing this for 2 instead of 3, because that would have made it easier on me, right? Build myself some dividing lines in here. Excuse me. right. So that's the first derivatives. Now second derivatives, well, this one's easy. I like this one right here. This one's nice. I could do this one all day long. Keep differentiating. Yay. I got to think about it. So the derivative of the polynomial gives me a lambda, and then I get plus lambda times 1 plus t lambda, which ends up being lambda plus t lambda squared. So after the dust settles, I've got 2 lambda plus lambda t squared, I think. You guys work it out and double check me on that, yeah? If I differentiate this, on the other hand, I get a 2 plus 2t lambda plus 2t lambda plus t squared lambda squared from the product rule, all times e to the lambda t. I got some good news. A property of the determinant is that it's multilinear. That means that you can pull scalars, in this case the function e to the lambda t, out of the columns or the rows. So since I've got e to the lambda t multiplying everything here, and everything here, the sum total of that is that I can pull out a lambda t cubed out front, which will make our life a little bit less annoying. Then I've got 1 lambda squared t, 1 plus lambda t, 2 plus lambda t squared.
I think the lambda should be squared instead of the t. Right? Was the other one that you just wrote out?
Oh yes, thank you. Thank you. And then this one, we've got t squared. We've got 2t plus t squared lambda. These two combine, right? So we get 2 plus 4t lambda. I'm regretting doing this at the moment. T squared lambda squared. I should have just done this for 2. We've been done 5 minutes ago. Let's see here. So then, well, it is what it is, I suppose. Oh. Well. I know how to make it nicer. So one of the things we'll learn about determinants if you take Math 221 is that you can do row operations without changing the determinant. So like I can, now let's not do that, I will resist the urge. We'll just calculate it. So we've got 1 times 1 plus, I'd really like to bail on this calculation at the moment. Permission to bail. Let's see here, 2 plus 4t lambda plus t squared lambda squared. All right, and then you got minus t times lambda times 2 plus 4t lambda plus t squared lambda squared. That's my, so this is, I'll do some color coding here, let you know what's going on. So I'm doing this times this subdeterminant, that's these guys. Then I'm doing this times these guys, which is this. And then finally, last but not least, I have plus t squared times this subdeterminant, which is lambda times, so I got lambda times, I won't multiply, I'm trying not to multiply them out. I'm trying to just like write down what they are rather than doing any kind of like steps in my head so you can see better what's going on here, you know? But there it is. And so if I'm doing a calculation like this, here's how I do it, guys. I go like order by order. So I've got my e to the t. Well, I could just write e to the 3 lambda t out front, right? And what's the highest order we have here? All right, so t cubed. What are the coefficients? How many t cubes do we got? Here and here, right? So that gives us a what? Lambda cubed t cubed, right? So I get a lambda cubed from that. That's it for this first term. How about the next one? Any lambda cubed in here? Oh, look at that right here. This lambda times that lambda squared gives me a lambda cubed. This time we got a minus, so we got a minus lambda cubed from the middle determinant. Is there any lambda cubed down in here? Yes, sir, there is right here. So we've got a minus what? Minus lambda cubed t cubed right there, right? Yeah, so looks like we've got, am I right? So we've got a net of lambda cubed there.
There's another one.
There's another one?
Yeah, first term of the...
Another one. Is that t cubed too?
Yeah.
Oh yeah, cool. So, oh, I like that. Goodness gracious. Well, that looks like a big fat 0 to me. Right? 0. And then let's look at the t squared terms. What do we got for t squared? We've got this 1 times t squared. That gives me a lambda squared, right? But we've also got this right here, which gives me a 4 lambda squared t squared. 1 plus 4 is 5. 5 lambda squared from the first determinant. Next up here, I've got 4, I think just minus 4 from the middle one, right? How many lambda squared? I got a 2t squared, looks like 2 lambda. I'm looking for t squared terms, right? So anything constant in here, I've got a 2 lambda and a minus lambda squared, right? So I've got plus 2 lambda minus lambda squared, is that right? You guys have to keep me honest. How many total terms are we looking for here? Well, let me not. I already combined some, I can't count. So did I get everything here? If you see anything in the t squared realm which I haven't taken account of, please let me know. Things are closer than they appear up on the board. So t, what we got? We've got a 2 lambda here, and plus the 4, which gives me 6 lambda t for that term. How about over here? I've got a minus 2t lambda, so minus 2 lambda. Down here, no dice, right? Because multiplication by t squared puts this out of the running for the t coefficient. So it looks like I got that. And then how about the constant terms? I got a 2. That's all I got, I think. Is that right? Yeah, that feels wrong. 2. I think that's it. So what do we got all together here? E to the 3 lambda t. This is 0. What happened about what about up here? This was also what? I think this is also 0, right? Because I get, oh, wait a minute, is it? Oh, I got 7 minus, I get 2 lambda squared? Is that right?
Yeah.
Because I got 7 minus 5, which is 2. So I got 2 lambda squared plus 4 lambda plus 2, right? Which is e to the 3 lambda t times what? Times 2 times lambda plus 1 squared. Or did I get that? Wait a minute, hold on a second. Is that lambda plus 1 squared?
In the t squared term, I assume that's supposed to be 2 lambda squared.
2 lambda squared. Where, which one? Here? This one?
Yeah, the one above that. I assume that's just missed the squared.
Where did I miss it? Here? Oh. Is that right? What? Oh, I can't just drop the squares. I'm just dropping the, I'm dropping the t's. I'm an idiot. Like, good grief. Come on, guys. Let me do that. So, listen, I'm going to stop right there. The point is that this is not equal to 0. I mean, we could clean it up a bit, but I'm kind of out of board space, and I'm definitely losing some of your patience. So let's stop there. So I think, yeah, all right. Sorry. Didn't want that for to go on so long, but it is what it is. So all I was trying to establish there, guys, is that in fact the solution set we're looking at here is linearly independent. Now, I could show that to you through more direct methods. Maybe I should just do that. Or maybe I should just assume linear independence and you'll believe me, I guess. But here, I can show you. Here's a method to prove linear independence. Suppose this argument was like way easier. I should have done this to start with. Suppose you got C1 e to the lambda t plus C2 t e to the lambda t plus da 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 plus Cm t to the m minus 1 e to the lambda t equals to 0. The definition of linear independence is that if we take that linear combination equal to 0, and we can show that the coefficients are all 0, that gives us linear independence. We can also, foolishly, try to calculate the Wronskian directly in this context, like I tried to do today. Even for 3, it's onerous. This argument, on the other hand, will be somewhat easy. So by construction, right? Operate by d minus lambda to the m minus 1 power. If we feed that t to the j, e to the lambda j, e to the lambda t rather, we get 0 for j equals to 0, 1, all the way up to m minus 2. That's what the solution set does. It kills off all of the first things. So if I take this equation here, all right, let me call it star. So if I operate on star by this, we get just d minus lambda to the m minus 1 power acting on Cm t to the m minus 1 e to the lambda t equals to 0. Because that operator kills the first terms, everything up to the last term that is going to differentiate to 0. And then what happens when you do this on that? What happens there? It might be helpful to see like a particular instance of this. So for example, if I took d minus lambda squared and I was to operate on, you know, I think my counting's off. What did I say? I shouldn't have done. Oh no, it's fine, it's fine. So if I do this on, oh, sorry guys, C2 d squared e to lambda t, what happens? How does this go? We have d minus lambda times the derivative, C2 times derivative with respect to time of t squared e to the lambda t minus lambda e to lambda t. How's that differentiation go, though? Well, so this gives me, you know, 2c2t e to the lambda t plus c2t squared e to the lambda t. I lost my c2 and my t squared over here, guys. Don't let me do that. So c2 t squared e lambda t. So those, oh yeah, and I'm differentiating e to the lambda here, so I have a multiplication by lambda. But then I've got minus lambda c2t squared e to the lambda t. The point is that these cancel, and we're just left with that. But now we differentiate again. What happens? We get, you know, the derivative of the first term, it's product rule, so I've got 2c1 e to the lambda t plus 2c2t lambda e to the lambda t from the product rule in the first term, and then I've got minus lambda times 2c2t e to the lambda t. Those last two terms cancel again. And we're just left with this. All right. So this same thing will happen with the mth order, the m minus 1th order derivative. Like what we're going to get in this calculation, if we work through it, it gives us that we get, if I remember right, m minus 1 factorial times cm e to the lambda t is equal to 0. Because when you do m minus 1 differentiations, you keep differentiating. And what happens as you do that differentiation is all the higher order stuff cancels out like we just saw here. Like the t squared with the t squared, and then it drops down, the next differentiation drops the t with the t. So that same pattern happens when you work out the line above. And then and the long and short of it is that you end up with m minus 1 factorial times cm. But what's this tell us about cm? It tells us that cm is equal to 0, right? But the thing is, if we can do this argument for the top coefficient, we can just as well repeat the argument if we multiply instead of by m minus 1 power, if we multiply by the m minus 2 power, right? The same argument going through with m minus 2 power will show us that cm minus 2 equals to 0. So similarly, cm minus 2 equals to, m minus 1 rather, equals to 0. And so forth and so on until we get to c2 equal to 0 and c1 equals to 0. Which then proves that, in fact, yes, this is a linearly independent set of functions, right? Which you might have just believed me to start with anyway. You're like, you don't need to prove this. Maybe that's true. But I did. So, all right. So now that we have this solution set, let's put it into practice. So what I want to do here, guys, is ask you some, we worked out some like forward problems last class, right? We solved some differential equations. Now I want to ask you guys if you can perhaps unsolve some differential equations. So I'm going to ask you a slightly different question. All right, but I'll set you up. Example 1. Suppose we've got y prime 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 plus, well, let's say minus 3y prime prime, 3y prime prime plus 3y prime minus y equals to 0. All right, so that gives us lambda cubed minus 3 lambda squared plus 3 lambda minus 1 equals to 0, which is lambda minus 1 cubed equals to 0 as it happens. So my solution then has the following form: c1 e to the t plus c2 t e to the t plus c3 t squared e to the t. And I know that's a fundamental solution set because of the pain and suffering you guys just endured. Right? Those are linearly independent functions, and this is a order 3 problem. There's the general solution. Yay, we're done. So here's the inverse question I have for you guys. Find lowest order ODE in operator notation which has t squared e to the t as solution. So in other words, I want you to tell me L such that L of y equals to 0 has, you know, that as a solution. What's my L? L equal to what? Oh, all right, fine. Example 3. Find L such that L of y equals to 0 has solutions y equals cosine t and y equals to t e to the 3t sine t. All right, can we finish this first problem here? What we got? Like the answer is right here. D cubed, what? Plus, or rather minus 3d squared plus 3d minus 1, or if you want to be civilized, you could say d minus 1 cubed. That is the smallest order differential equation, which will pick up t squared e to the t as its solution. All I'm doing is reading my solution backwards. So this second example, third example I've given you here, this comes from a d squared plus 1. This comes from, well, let me write it out in steps here. Lambda equals to 3 plus or minus I, but let's say plus I. So like, you know, fun fact, I guess. If you have d minus alpha squared plus beta squared, this has y equals to e to the alpha t cos beta t, and y equals to e to the alpha t sine of beta t as solutions, since e to the alpha plus I beta t equals to cosine, that was alpha, equals e to the alpha t cos beta t plus I e to the alpha t sine beta t. Right. And if you're quadratic, right, if you have a quadratic which is like that, it cannot be factored in the reals, you have a complex solution, all right? Now, this comes from lambda equals 3 plus I, but there's a t here, right? What's that mean?
We have algebraic multiplicity too.
That's right. This has got to be repeated, right? So what I cipher from this is that I can choose L equal to d squared plus 1, right? And in order to pick up that as a solution, I need a d minus 3 squared plus 1, but that has to be squared in order to pick up the t solution there. And so if my differential operator is d squared plus 1 times d squared, you know, minus 6d plus 10, all squared, you don't have to actually multiply it out, but this defines a sixth order operator whose solution set will include the cosine and sine times exponential times t term that we want. Yep. Example 4. Suppose you want to solve y prime prime plus 6y prime plus, oh, I don't know, 37 y equals to 0. How do you do this? Well, there are several ways, but one way we could do this is convert it to an operator equation. This is d squared plus 6d plus 37. Y equals to 0. Or, what's the other choice? Or you could look at it instead. This is the one path. You could go this path, right? The other path is we could go back to like what we were doing before. Look at the characteristic equation. So I'll let you guys choose for this one. Which way do you want me to, which path do you want me to go down to for this one? The characteristic equation? Okay, we'll do that. So how should I solve that? I have lambda plus 3 squared minus 9 plus 37 equals to 0. What am I doing? I am completing the square. And so that gives me lambda plus 3 squared, plus 26, I think? 28? 28, yeah, 28 equals to 0. That tells me that lambda is minus 3 plus or minus I times the square root of 28. Therefore, y is c1 e to the minus 3t cosine square root of 28t plus c2 e to the minus 3t sine of the square root of 28t. And there you go. That's your general solution right there. So, to recap, how we solve the nth order problem, there's a couple different things going on. The one is we can write down the characteristic equation, we factor it, and then for each root we get solution, right? If it's a complex root, we get a pair of real solutions by looking at the real and imaginary part. If it's a repeated root, we have to use the theorem that I've been deriving for the last class and a half, which is that we multiply by t or t squared and so forth in order to generate new solutions. And generally speaking, if you have an nth order problem, you're looking for n linearly independent solutions. The general solution is a linear combination thereof, right? So there's some interesting questions to ask here. One, of course, is just to find the general solution set like we've looked at a little bit. The other is to solve initial value problems. Like what if I gave you an initial position, initial velocity, we could solve those. It's kind of obvious what to do there, but these are trickier, right? Go the other way. You know, what differential equation takes something as a solution? It turns out that this is not just an idle curiosity. This will be the bedrock for our method for solving non-homogeneous problems next week. So we're going to need to do this inverse solving thing in order to set up particular solutions for the problem, as we'll see. But so like Monday, I'll give you a comprehensive quiz on like all of the different solution types. All right. So yeah, you have that to look forward. How about I give you a quiz just to turn it start a class? That'd be better. It's like you do work on it over the weekend. Sound good? Yeah, we'll do that. So you can expect that in your, you know. I'll make an announcement later once I've written it. So.
Like an in-class quiz or like another one where we do it?
It's take home. Yeah, yeah.
Like due Monday?
Due Monday, start class, yep.